so that during the live stream, my video does not overlap with the slides. So as I was saying earlier, I had some difficulty in the morning with my internet. So if my internet connection for some reason temporarily breaks, please stay online. I will be back in a few minutes. So having
Okay.
said that, I would like to thank the organizers for putting this together and giving me a chance to talk to you all. I'm told that I am talking to students who are mostly interested in biophysics or working with physics applications to biological systems. And I thought that one of the key areas, given the current compute environments, is to talk about building models and trying to um, use the compute resources that are available to us to solve these models and try to get some kind of useful information from them. So today's talk is based on on the subject of modeling biological systems. We will be talking about some first principles, which are very important in my opinion, and I will put some stress on them. We will then work our way towards basics of modeling. I will introduce some existing models, and we will also work through a use case where I will show you how to develop a model, for instance. And during the talk at various points, I will also refer to current challenges, what people get wrong, how to make sure that we are not abusing the model, and etc. So my introduction has already been given to you by Umar. My name is Ashar. I'm a senior postdoc at the Bioinformatics Institute at the Agency of Science, Technology and Research, ASTAR, in Singapore. I have a PhD in computational biochemistry, but most of my work that I've done so far, I have used physics applications extensively, and I've been applying that to biological systems for quite a number of years now. So with that, the first thing that I would like to discuss with all of you is the fact like is to talk about first principles. So when we use the word first principle, this is kind of a loaded term. And the reason why I use the word loaded is because as we have come along, as the human civilization has evolved and we have tried to understand the environment and the physical systems that we interact with on a daily basis, we have tried to understand them. And what has happened is that over a period of time, our understanding about the things that we are looking at or interacting with has improved. Now, if you go back a few hundred years, you will see that people used to understand things differently. Then, with the passage of time, as modern scientific methods came out, the understanding improved. And as the understanding improved, things connected with that understanding also improved. So, even today, if we say that we know everything about everything, that would be wrong. There is a continuous change in our understanding and our knowledge as we are progressing on a day by day basis. So when we talk about first principles are basically how well do you understand the system that you are looking at. We will talk about a few systems, but for now, just to give you a very rundown and a very simple example of first principles, let's take the example problem of water, right? So just imagine for a few minutes that you are somebody who has never seen water and you don't know about the biochemical or the biophysical properties of water, right? So you are very new to the concept of water and you realize that if you take fire, for example, and if you put it under the water after some time will start to boil, right? And then if the fire is not there, then the water does not boil. So your understanding or the scope of your understanding related to water is limited to your observation that if you put fire and water together, like for example, the water is in a pot and the underneath the pot there is fire, that after some time, what will happen is that the water will start to boil, right? So your observation of the physical system is limited to just the fact that if the fire is present, the water will boil. If the fire is not present, then the water will not boil, right? So this was your understanding at the start, right? With the passage of time, what ends up happening is that somebody comes along and they say that if you use a stronger flame or if you use a bigger flame, then the water will boil faster. And if the flame is weaker, the water will take longer to boil. I mean, these are empirical observations, right? So now what has happened is that not only do you understand that the fire is necessary, but you also understand that there is a certain amount of strength in terms of heat that is needed from the flame to be able to boil the water in a given amount of time, right? So now with the introduction of new variables, like previously the variable was just fire on, fire off, right? So now not only does the fire have to be turned on, but it also has to be at a certain level for you to achieve boiling in a certain amount of time, right? Now, think about this. Think about that a few more days or a few more years or a few more centuries have passed, and somebody comes along and they say that, water can be of different types, right? You can have hard water, you can have normal water, you can have water which is contaminated with certain pollutants, you can have mineral water, you can have pure water, right? And all of these types of water or yeah, so all of these types of water will have slightly different boiling points, right? So pure water boils at around 100 degrees, like at exactly 100 degrees, right? But if you add impurities to it, what is going to happen is that the boiling point is going to get affected, right? So first of all, your understanding was limited that fire on, fire off boils water. Fire off does not boil water. Then your understanding improved, and you realize that, as you go on, you realize that the amount of heat being produced by the flame is also an important variable, and it controls how fast or how slow the water is going to reach boiling, right? And then you were introduced to a third parameter, which is the parameter of purity of water. And depending on the purity level, your boiling point will, like obviously if the boiling point is slightly higher than 100, then it will take you longer to reach that boiling point, right? So what has happened in the course of the last 5 minutes is that I have tried to explain to you what first principles are, right? So when you were limited to only knowing about the one variable, your understanding was that, it is only the fire that affects the boiling. But then your understanding improved, and with the passage of time, things got better and better. Now, first principle refers to the original, most fundamental level of truth, or the most fundamental of description of a system, right? And I might be wrong when I say this, but I don't think that we fully understand or fully comprehend any system that we are currently interacting with. What we do know is that we have sufficient amount of understanding, which is not complete by any extent of the way. We just have sufficient understanding of physical systems to put them to good use. Like, for example, we know enough about aerodynamics to make a plane, put some fuel in it, let the engine run, and the plane flies, right? So we know sufficient amount of detail about how to make a plane fly, like about aerodynamics, right? And we don't know enough to send rockets into space, for example. So just enough understanding to make the system work to our advantage, right? So when we talk about first principles is knowing everything about your system, knowing at the most fundamental level all the things that can possibly impact your system that you are observing. Okay, so this is what first principles are. And I will show you in the next couple of slides why first principles are important when you are modeling or building models, for example. Okay, so let's work with that molecular example of water, right? So we talked about previously, we talked about three variables. We talked about fire, we talked about the purity of water, and we talked about how long is the water being exposed. But right, but at the if you start decomposing what water is just not liquid, right? Water contains molecules. So when you look at these molecules have certain biochemical properties, right? So you have a dipole or biophysical properties depending on which area you're in. So, for example, water molecules have dipole moments, right? And based on these dipole moments, what happens is that water assumes a certain arrangement when it's in a liquid state. And when you add impurities to it, these arrangements are affected, which consequently affect how water, at what temperature water is going to boil, right? So again, with more information that you have about your system, your understanding improves. And as your understanding improves, you go closer and closer to the first principles, right? So for example, a molecule in itself is not the ground level of reality, right? So molecules are made up of atoms. Atoms have like electrons, and they have a nucleus. And then inside the nucleus, you have protons. And then inside the protons, you have, uh, uh, from our current understanding, like if you go back, like let's say 100 years, we did not know about, for example, these three levels, right? Maybe we knew about molecules, but shorter than that, we did not know about the atomic structure. That happened in the 20th century. We found out about the nucleus, the proton, and later on we also came across. And this is the existing standard model of elementary particles, but by no means is this final, right? Maybe in 5 years, 10 years, somebody will discover a new theory, will put forward a new theory, which will describe our existence in a much better way, right? So which will describe the universe in a much better way. And what will end up happening is that this model, the standard model of elementary particles, will change. So for now, we believe that this is the ground level, right? But we are increasingly finding evidence that this is not the case, right? So when we talk about first principles are about the knowing the absolute ground level reality, right? So until and unless you don't know that, anything that you are going to extract from your physical system is going to be not complete, obviously, because you don't have all the information regarding your system, right? So even though with the limited amount of information, you can still use it to your advantage. We can still make planes fly, right? We can still make certain kinds of medicine, right? We can still see how bacteria infect living organisms, and we can still understand that putting antibiotics into those systems is going to actually impede the growth of bacteria, right? But at the ground level, we don't have a complete understanding, for example, which is why not all antibiotics work with all individuals or work with all strains of bacteria, right? So there are some bacteria that might be affected by an antibiotic, and there are some bacteria that might not be affected by a certain antibiotic, right? So our understanding is completely limited in those contexts. And if it was complete, then we will be able to find solutions which are applicable across the board, and like there are no errors or there are no rooms for improvement. But that I don't think that will ever happen. As a scientist, I don't think we will reach that stage. I mean, we hope to reach that stage, but I am skeptical that we will reach it anytime soon, given the current state that we are in. So having said that, first principles are important about for models, for us to understand how to explain our physical systems. But let's not, take a step to the side, for example, and try and see what exactly is a model, right? Now, there are several different kinds of models. I will touch on two or three of them, but the kind of modeling that I am going to limit to in this talk is mostly going to be on mathematical modeling, but we will touch on some other kinds of models as we go along. Okay. By the way, if there are any questions or if something is not clear, please feel free to interrupt. and ask questions. Otherwise, I will just keep on talking. Otherwise, there is also a dedicated time for Q&A at the end. So if you don't want to talk in the middle, that's also okay. You can ask your questions at the end of this talk. So let's have a look at what do models look like, right? We've been talking about first principles. We've been talking about physical systems that are explained by those first principles. And now we're going to look at how do we look at a physical system and how do we actually turn it into a model. So I'm going to use a very simple example of things that you use in every day. Like, for example, I sometimes wake up late and then I have a meeting in the office, and then I start thinking that if I take bus A, which goes through route A, I will reach my office in 30 minutes. But if I take bus B, which goes through a different route, it might get stuck in traffic, right? So this is an interpretive statement. And when I am saying this statement is actually based on a mental model in my head, which actually tells me which path to take to get to the office in the quickest amount of time or in the shortest amount of time, right? So I am basically using a model to make this prediction. So this line, this interpreted statement, is a prediction that if bus A is taken, which takes route A, I will get to the office in time, right? So when you use models, you're basically, what you are trying to do is you're trying to make a prediction. So what is the model from which you can get a statement like this? You don't have to just limit yourself to statement like this, right? The statement can be of any different type. I mean, I'm just using reaching the office as an example, but I will show you other examples where other kinds of models are being used. But for now, while we are on our path to looking at what models look like and how does one make one, I think these examples are sufficient for this case. So let's take the example of a car, for example, right? So the car is going at a speed of 5 kilometers per hour, right? So this is an observation. Like, if you can look at the speedometer, and it will show the needle at around 5 kilometers per hour. And then you can say that if the car keeps traveling at 5 kilometers per hour, after 1 hour, it would have traveled 5 kilometers. Okay. After 2 hours, it would have traveled 10 kilometers. And after 3 hours, it would have traveled 15 kilometers. Now, these are very simple statements, right? But there is a mathematical model which you are actually using to come up with these numbers. Okay. So what is that mathematical model? So you will notice that there are units, 5 kilometers per hour, right? So if you're traveling at 5 kilometers per every hour, then for 2 hours you would have traveled 10 kilometers, and for 3 hours you simply multiply it by 3 and you get the number 15, right? But let's stop here and let's try and think about that. Does a car always travel at 5 kilometers per hour? I mean, even if that's its maximum speed, or if that's the speed limit on the road, then you should always think about that that the car is going to stop at traffic lights, and there are obviously going to be pedestrians. So on the crossing, where the car would actually have to stop. So there are going to be periods when the car is accelerating and when the car is decelerating. But in the model that we just used, we only used two parameters. We used the speed and we used the number of or the time, right? But so accelerating and decelerating is not used in our equation or in our model, which is why our model will not give us 100% accurate results, right? And the reason for that is because we are not looking at a complete description of the system, right? So the way to do that is to use Newtonian equations of motion, for example. And there, I haven't actually written what each of these terms is, but S is basically the distance covered, U is the speed, and T is the time. So if you are only looking at this first part, S equals UT, that is what we were doing up here, right? So when we were doing this, we were not taking into account any acceleration. But when you look at Newtonian equations, right? So Newtonian equation has an element of an add-on half a t squared. So a is the acceleration. So now what we have done is we have actually taken into account the cases of the traffic lights and the pedestrians. Obviously, this is not a complete description, because at the traffic light, you just don't slow down, you actually come to a stop, right? So even for the pedestrians, you don't actually just slow down, you actually come to a stop, then you start accelerating and reach your speed. But the idea here is to show you that there are going to be some models which are going to be accurate to a certain degree, right? Then there are going to be some other models which are going to be better than what we were doing up here. And then, of course, there are going to be other models which are going to be even better, right? So, for example, you should always be asking this question that, are you satisfied with the kind of results that you're getting from this model, right? Is there room to improve? Do you want to improve? Because maybe the kind of results that you're getting are sufficient. For example, let's just step back now and let's think about the door of the car, or the tire of the car, or the or the window glass of the car, or these lights. Now, as a whole, the car is made up of atoms, right? And there are millions upon billions of atoms that are coming together to make the whole car. But when we talk about that the car is traveling at 5 kilometers per hour, how much distance will the car have covered in 1 hour? We do not want to track each individual atom. I mean, we can do that if we had like a a very super computer. We might be able to keep a track on each of the individual atoms. Or if you're trying to be fancy, go down to the quantum level and keep a track of each of the quantum particles that make up the car, right? You can do that. But doing that will not improve your answer, because just looking at the car as a whole is sufficient for you to apply this model to get this answer, which would roughly be correct, right? You do not need to go down to the atomic level to see how the atoms are moving forward. Okay, so there is always going to be room for improvement. There is always going to be a better model that explains the result better. Do you want that model, or are you satisfied with that? You just want the car to go from here to here, and you want to find out that if the car is traveling at 5 kilometers per hour, how long will it take for the car to travel 5 kilometers? Or maybe you want to express the statement in a different way, that if the car is traveling at 5 kilometers per hour, how much will it have traveled in 1 hour, right? So this is a very simple rundown example of what is a model, what does a model look like, and what are we going to use it to do. Okay. It is also important that while models are used to make predictions, we should always be careful that, can a model that was invented or developed for the green car be used on the red truck? Okay. Obviously it can be, but I'm just trying to tell you this thing that, you're trying to make predictions about a car, you use Newtonian equations. Is it okay? You should always ask this question: is it okay to take a model developed for something else to give and apply it onto something else, right? Now, by looks of it, the green car is different than this red truck. Okay. But what are we trying to do? For us, for our purpose, we can ignore that this is a car or that this is a truck. We can think of both of these as a solid block of metal. We don't really care whether it has 4 tires or whether it has 20 tires. I mean, it will make a difference if you are trying to work into it fuel consumption, or if you're trying to be very accurate, maybe trucks will take longer to cover 5 kilometers because they have higher periods of deceleration or acceleration. But for normal everyday calculations, when you talk about a pickup truck, for example, you can apply the same equations of Newtonian equations of motion and be able to work out how much distance would it have traveled, right? But the idea here is just to stress the importance that if a model is made for system A and you are trying to apply it onto system B, you should always be careful that are there parameters inside this model which may be different when you apply it onto a truck, right? Because a lot of people, when we go to the scientific literature, make this mistake that a model which is not suitable for a system, they have applied it to that without, because what has happened over the last 10, 15, 20 years is that every time a new model comes out, for example, somebody develops it into a program which people can easily install on their computers. And people who are not programmers, they make this mistake very often, that they will assume incorrectly that if I have this program, I can put in any data into it and get my predictions. Okay. But this approach usually creates bad results. And you should always avoid getting into situations like this where this might happen to you. Okay, so don't deal with models as black boxes. Try to spend some time on the original paper or the original text that surrounded your model, and see if they have mentioned any limitations of the model which might impair your application to a different truck. Okay, so now, having talked about one kind of model, which is the Newtonian equations of motion, physics is literally full of models. Okay, so I'm going to give you a few more examples. So here I'm showing you a model which predicts how long does it take for a particular uh, uh, for a particular planet to complete its orbit. Okay, and sorry, to explain this, too sensitive, the mouse. So yeah, so to explain this, Kepler's law are there. So Kepler's third law looks something like this. We're not going to go into the details of this because this is beyond the scope of today's talk on biological systems, which I will come to shortly. But just wanted to illustrate that you can think about planets. You can think about planets moving in their orbits, and that orbital motion, you can make predictions, right? You can make predictions as to what is the mass of the star and what is the mass of the planet. And if you have these two variables and obviously the size of the size of the semi-major axis in this case, you should be able to work out the time required for the planet to complete an orbit. Okay, so similarly, you have Newtonian law of gravitation, which basically is, you should have read this, you should have studied this in high school, which is basically that if there are two massive objects, M1 and M2, and if there is a certain distance between them, there will be a force acting, a force of attraction, which is actually pulling the two things together. Okay, so this is another example of a model. If we move to a completely different direction, weather prediction is also based on mathematical models, right? So when you are looking at predicting weathers, for example, weather forecast, for example, you can go, you can, this becomes quite complicated, right? But if you break it down, what you are essentially doing is that you are looking at all the things that can affect the weather, right? So there might be one direction of wind, another direction of wind, there is temperature, there is humidity, there is continuity of mass, there is surface pressure, and there are like a whole other set of variables. And the more the variables you put in, the better your prediction is going to get, as long as they are relevant, right? Just like I give you the example of water boiling, if you want to be specific, you need to know how much heat the flame is producing. You need to know the quality of the water that you are dealing with. Okay, so the more you know about your system, the more accurately you can predict how long it is going to take for the water to boil. Similarly, in this case, the more you know about what are the possible things that affect weather, and then use those as variables inside your forecast mechanism, will give you a better prediction. Okay, so this is another example where models can be used. But this leads me to like sort of a concluding thought, uh, which came from a famous statistician, who said that all models are wrong, but some models are useful. And this goes back to the same example which I gave you, that we don't have a complete understanding of aerodynamics, for instance, but we know enough about aerodynamics to make a plane and make it fly in the air, right? Maybe that was our only intention to know. So maybe we don't want to know more, right? But when you look at this statement is basically talking about that if you are doing weather forecasting, for example, and if you don't use all the parameters, or if you use them in the wrong way, then obviously your answer will be wrong. Okay. So just bear this in mind that I will discuss this in more details in a few slides, but bear in mind that models have limitations. They are made for certain things. Know the limitations of the models before you actually apply it onto your system. Okay. So having looked at what models are, now we're going to spend some time and see how do we make a model, right? So we've looked at all of these equations, and we have looked at a few different systems. But to give students a better understanding of what is like how does one go around making a model, okay? So I'm going to use a biological example of bacterial growth. Okay, so what happens in this instance is you take some bacteria. Let's suppose you take one bacterial cell, and what you do is you put it in a growth medium. So a growth medium is a medium which has the nutrients required for the bacteria to actually grow, right? So what happens is that the bacteria will start growing. So one bacterial cell will be divided into two, two will become four, four will become, so each of the four cells will make a copy, sorry, not make a copy, but more like divide into two. So four become eight. Then each of the eight become two. So they in total they become 16. Okay. Now, for people who work in a wet lab, they have seen this, that if you put the bacteria in a growth medium, there is a period of time when nothing happens. After a period of time, the bacterial population goes into a growth phase. So this line, which is labeled as log or exponential phase, is where the population started at a low number, which is given on the y-axis, and went to a higher number. After this point, what happens is that there are so many bacteria in there that all the nutrients in which they were growing have been used up, or there is no more space for which in which for the bacteria to grow, or there could be a number of other factors. And what ends up happening is that the growth stops and there is a stationary phase. So the bacteria are all there, but they are no longer dividing into, each bacteria is no longer dividing into two, because there is not enough nutrients or not enough space, or whatever the reason is, right? And then what happens is that after this period of time, because there is no more media and there is no more growth, the bacteria will start to die out, right? Now, on the x-axis, you have time. So some student, some PhD student or some master level research student has gone into the lab and has measured these intensities, these population sizes at different points of time, right? And based on their observation, they have made two-column table. In one column, they have time, and in the other column, they have population. And then what they do is they put the population, they plot it, and this is the curve that comes out. Okay, so this curve is based on a real world phenomena which some researcher has observed, recorded, and analyzed. Okay. So when they have observed it, they saw bacteria were growing. They measured the bacterial growth, and they recorded it into tables. And then what they did was, in the analysis part, they actually took that table and they made a plot. So once they made a plot, they realized, that what was happening in each of these. They gave it a possible explanation, right? So now, what is important to remember here is that this graph is only suitable for the bacteria that the researcher was looking at. Now, there are different kinds of bacteria, and different kinds of bacteria have different growth characteristics, right? So not all bacteria grow at the same rate. Not all bacteria will consume certain nutritional media in the same way. I mean, a bacteria will always, when it's time for it to grow or divide, it will go from 1 to 2. But there are some bacteria which might divide after 20 minutes, and there are some bacteria which might divide after. Well, I know about the 20 minutes because I know E. coli, but I don't know. Maybe some bacteria divided in 1 hour, maybe some bacteria divided in 3 hours. So they will have different characteristic rates. So the shape of the graph will be slightly different, right? But what we can take away from here is that we're going to look at this graph and we're going to try and build a model for it, okay? Which is the purpose of this exercise. So in here, we look at these vertical lines, and these vertical lines separate different phases. We are only going to look at the exponential phase for now. And what we're going to do is we are going to try and find a line which comes closest to this particular line. Okay. So if you draw a straight line, for example, y equals x, it looks like this. This is a straight line. So for every unit increase in x, you have a unit increase in y. And then these remaining have certain powers of x. Now, these certain power of x will actually affect the gradient of this line. Okay. Now, we're not going to go into the details of which will exactly match this part, but people have already done this, right? And what they have concluded is that this equation, P equals A E K T, is something that best fits this log phase for all kinds of bacteria, not just E. coli or not just bacteria A or bacteria B, but most bacterial growth, when the bacterial growth is in its log phase, can be explained by this particular model. So P actually represents the population of the bacteria. A is a constant. So basically, it is the number of bacteria when you start your experiment. Okay. E is the exponent. K and T are actually positive constant of growth, and the time in hours. So what is the purpose of this model? Why have we modeled it? What is the benefit of this model, right? So one thing is, yes, it explains the bacterial growth rate, but the other thing it does is it can help predict things for us, right? So for example, if you know A, E, K, and T, you can change the value of T, right? So you can put in T 1 hour, 2 hour, 3 hour, 4 hour, 5 hour. And at each time you change the value of T, you will get a value for P, which is the population size of bacteria. Now, there are two things. If you're growing bacteria in your lab, you can do two things. You can either check every 5 minutes to see how much population is in your sample, right? Now that will take too much time, and the amount of error that you have in your observation will grow. Okay. On the other hand, you can use this model and you can say that, oh, I need my bacteria to be of this. Maybe you want 8, or maybe you want 6, or maybe you want 4. Okay, on this y-axis scale, right? So that is your desired population. then what you can do is you can find out the time t it takes for the bacteria from where you started off at time t equals 0, A. How long will it take for you to reach a certain population size? So many times when you are in an experimental lab to run an experiment, you need a certain amount of bacteria, and you need the bacteria to grow to that size or the colony to become a certain size. Okay. Now you can do it the hard way. You can look at it every 5 minutes, every 10 minutes, every day, and make observations and record those observations, or you can just use the mathematical model. Okay. So this is the purpose of the mathematical model here, that some poor student will not have to look at the growth every 5 minutes. They can just use this model, fill up the parameters, and find out how long will it take for it to reach a certain size. But remember that these parameters will have different values for different bacteria. And now you should step back and think about what I said earlier, that if a model is developed for bacteria, do you want to use it for viruses? Like, can you apply this model to estimate the growth of a virus? And the answer is no, you cannot. Why? Because bacteria go from 1 to 2, right? So if you take a bacterial cell, if you give it sufficient nutritional media, it will divide into 2 cells. But if you take a single particle of a virus, a single viral particle, and if you allow it to replicate, it will make hundreds of thousands, if not millions and billions of copies of itself. So if you look at the pathway of how a viral particle replicates, it enters into a cell, it makes millions of copies of itself, and then each of those copies goes and infects another cell. So the model for viral growth will be different from this one. Okay, just wanted to put this out there. So now there are so we have only looked at making a model for bacterial growth. Okay, but there are going to be several different kinds of models. Like, for example, there are physiological models, which explains, for one of them, which I've included here, is something that explains how neurons work, right? So I'm going to show you this as an example, but there are other examples of models. Like, for example, you can have Starling murmurations, bacterial growth, which we just talked about. You can have population dynamics, and I'll touch a brief on these in a few seconds. But what I want to do now is I want to show you a video so I'm going to share my sound, share computer sound. Oh, so I'm just going to type in the password here. So how
do you feel now?
Did you all hear that? Can somebody say in the chat that they can hear my?
Yes, we can hear that.
Perfect. Okay, so I'm gonna rewind this and I'm gonna play it out again. So I want you to look at this video and then I will explain what is happening.
So how do you feel now compared to 2.5 years ago?
It's a year ago I couldn't scratch the top of my head, and today I get up, I do all my ADLs and can walk and exercise.
Okay, so this was a very short video. Obviously, you can look up what deep brain stimulation is. But what is important to remember here is that what is happening. So in this case, this is a patient who has Parkinson's. And what has happened is that by understanding how neurons work, how neurons fire, you might have heard of a pacemaker for the heart. So if the heart has irregular beats, you can put a pacemaker on the heart and the heart will start to beat with a normal rhythm. Just like that, there are centers in the brain which can actually mess up. I mean, if they start misfiring, they can actually mess up how your body responds, right? And Parkinson's disease is a classical example of that. So you can take a neural pacemaker or basically a deep brain stimulation device, and put it in the center of the brain, where what will happen is that it will control the way in which that center of the brain is firing. And you can see that the person on the left is the same man as the person on the right. The person on the left is when he came in for the treatment, and you saw that he had a lot of tremors. Now, this is a disease that is usually found in seniors. So it's a neurodegenerative disorder. I think it is, and it badly affects the quality of life, right? But by understanding or by modeling how neurons work, we have understood how they work, and by understanding how they work, we have been able to translate that understanding into a device which has been put into the person's brain. And as a result, you can see that he no longer has those tremors, and he can go back to living his life in a very normal way, well, sort of. Okay, because he still has that device attached to him. So it's not exactly back to normal, but it is much better than when he was when he started before he underwent the treatment, right? So again,
So how
modeling
do you
is
feel
a
now?
very important thing. Modeling helps us understand physical systems. So now you can see here that there is a kind of bird called starlings. So starlings fly around in these formations, which are called murmurations. And there has been a lot of work in trying to understand um, build models to explain what is happening here. Why are they flying like this? How are they making these beautiful formations in the sky, right? Because I don't think they have radio to contact each other, right? They're not talking to each other. They are just following a certain phenomena, and we don't yet understand exactly what it is. Maybe they're following the one in front of them. Maybe they're following the one behind them. But whatever is happening, um, we have to try and understand the model. We have to try and build the model. Okay, so that is one example. Bacterial growth, I've already talked about it. Population dynamics is where you predict population increases, because these are very important. By making models and making them accurately, we can predict how much hospital care will be required. So in this particular model, you can see that when the model starts out in 1985, I think, 1950, you will see that the highest age is 80 plus. But by the time it touches 2000, you have people who are reaching 100 plus years. Okay, so when you have more people who are old, it is going to require a lot of health care, right? So by modeling, you can actually make predictions about these things. So obviously, then there are models about genomic evolution. We're not going to go into the details of that because I cannot explain them using figures like this. So we're going to skip this, but I just wanted to make sure that you understood that there is something which can explain how genes evolve over time, or how nucleotides are substituted over time. And for people who have done sequence comparison using BLAST, they will know that they can apply PAM and blossom matrices. So those blossom matrices are basically, in other words, they are evolutionary models. Okay. So having said that, I would like to now take 1 or 2 minutes to explain the concept of biomimetics, right? So biomimetics is another area where you use things that exist in nature and translate them into technology. So for example, people have looked at lizard feet and found certain properties of the hair that is on those feet, and translated them into devices, into adhesives, and ways to heal the wound, not heal the wound, more like make stitches to close the wound. Okay, so that is technology translation by using biomimetics. So bio is bio, and mimetics is looking at something and translating that concept into a different area. Okay, so just like that, termites have a way in which they can create dirt mounds in the ground, and they have ways in which they can cool those mounds. And what architects have done is that they have looked at termite colonies and the way they are constructed, and translated that into developing designs for buildings, right? Another example of biomimetics is that whales have certain shapes along their fins, right? And what people have done is that taken that and made blades of wind turbines, and sorry, not they have actually done it for yeah, so they have translated that into wind turbine blades for better dynamics, right? So these are all things. So like I said in the beginning, models can be of many types. One of the classes that we are particularly focused in this talk are mathematical models, but there can be other kinds of models, right? So the other kind of models are where we've talked about just now about looking at lizard feet and translating that into adhesives, or looking at whales and translating what we have learned from that into design of wind turbine blades. Okay. Now, you will also know that there is another class of models, which are like, for example, when you have to develop new drugs. So you first test it in mice, right? So a mouse is a model to predict what will happen if you give a drug to a human. So if you give a drug to a mouse and the mouse survives, and whatever the drug is supposed to do, the drug does it, then chances are that because a mouse is a model for a human, you have just predicted using mouse what will happen if you give the drug to a human. Okay. So you have mouse models for the immune system. Then to see what happens in the human brain, you have a different animal model. Okay. So people who develop cosmetic products like lipsticks and other things to put on the face, for example, the cosmetic industry uses rabbits for testing, right? Because they are a better approximation, and they are obviously cheaper to make as well. So there is also the economic factor. But rabbits, for example, are used for cosmetic industry, for medical drugs, for diseases. You use mice model, and then you upscale that to using applying it to on chimpanzees because their genomic structure is more closer to humans, and then finally you actually come into humans, right? So there are different types of models, right? So let's now come down to applying modeling to molecular systems, okay? So when you talk about biomolecular systems, or when you talk about proteins in specific, or drug molecules that bind to proteins, or other assemblies, like for example, bilayers, what you are actually doing is you're taking each of the atoms that are making up a particular protein, and you give them XYZ coordinates. Okay. So when you do that, and then when you recreate a 3D drawing of that particular molecular system, it would look something like this, right? Now, it is important to remember that whenever you have a protein does not exist without thermal energy, right? There is always a protein is always going to be present in a certain organism which exists at a certain temperature, right? So, for example, humans have proteins, and we have a normal temperature of around 36 degree C, or about 98 degrees in Fahrenheit. Okay, so when we say that my temperature is 36 degrees, what I am saying is that if I look at all the molecules that are making me, right? Those molecules have atoms, and those atoms have certain kinetic energies. And when we talk about those kinetic energies, the average kinetic energy is what we refer to as the temperature. Okay. So temperature is not a quantity in itself. We have instruments that measure in degree C, or in Kelvin, or in degree F. But in reality, temperature is not a quantity. right? It is just a measure of the kinetic energy of the atoms that are making up a certain okay. So when I am existing at, if in under normal circumstances, when I am existing at 38 sorry, at 36 degree C, all of the atoms, be it of lipids, be it of any drugs that I have taken, or be it of proteins, are going to be in a state of motion because they have kinetic energy. Okay. So when we think about, we don't know this for sure because nobody can look at proteins, right? Because proteins are much, much smaller than the wavelength of light, which is why you can't look at a protein underneath a microscope, right? You need X-ray crystallography or you need NMR methods to actually actually find out the structure, right? So nobody's actually seen how proteins or the atoms that make up the proteins move. But again, just like before, I gave you examples that we know enough about aerodynamics to make a plane so that it can fly, or we know enough about a car, that if it's traveling at 5 kilometers per hour, that in 1 hour it will have covered 5 kilometers. What this basically means is that when we think about proteins, we assume that they will have motion like this, right? So you can have angles changing between atoms, you can have bond distances, and you can have rotations about bonds, right? And what we do is, by making these empirical assumptions, we try and replicate the behavior of proteins. And one method to do that inside a computer is called molecular dynamics simulations. Now, again, we don't know if this is how they are moving, but we assume that this is it. And then the next step, what we are going to do is, we are going to take a protein, do MD simulations, and take the same protein and go in the lab and work with that in the lab. And then we're going to get results from the computer simulations, and we're going to get results from our experiment. And we're going to try and compare. And for the last 40 years, people have been doing those comparisons, and they have found out that our assumption that this is how atoms inside protein structures are moving is fairly correct for the kind of work that we want to do, right? Not for all work, but for most work that we want to do, assuming that a protein is moving like this will give us results which are close to reality. Okay. So now there are different ways in which you can look at proteins. Okay. So this is one particular example where you're looking at a protein structure, you can wrap a surface around it, and then you can look at the wider assembly that is being constructed by each of these individual units, right? So in this case, this is just a fancy diagram for the HIV viral capsid. I don't have a reference for this. I did not make this. This comes from the VMD research group online. I think I had a reference, but for some reason, it is not showing here on the slide. Okay, so by visualizing, we can help build models. Okay, so for example, if you visualize this structure, you will know that this particular P24 unit is interacting with these two units, this unit, this unit, this unit, and this unit, right? And by looking at which side is facing what, you can actually try and understand how this interaction develops. And then once you have the understanding of how the interaction develops, you can actually create drugs which can disturb those interactions and prevent the viral capsid from forming. And you know that if the virus is not able to come back and make a capsid around it, it will not be able to be infective, right? And it will be destroyed. So one way of fighting with HIV is to understand by looking at these protein structures, right? So now, as I just mentioned about molecular dynamic simulations, let me just show you an animation, actually a video. So this is a video that comes out of the Australian Institute, CSIRO, in particular Data 61. where they have looked at the COVID-19 coronavirus interaction with the human receptor. So ACE2, this golden protein comes from humans, and this bottom part, out of which this pink part is shown here only, you have the spike protein from the coronavirus. And you will notice that at the interface, there are a lot of amino acids that are interacting. By doing MD simulations and by looking at which amino acids are interacting, we can develop drugs which can go in and bind to the pink protein, which is shown covered here in blue, in a blue surface. And if you're able to block the spike protein, for example, the coronavirus will not be able to enter the cell and make copies of itself, which means that you will not get sick. Okay. So this is one way in which molecular dynamics can help. Another way in which molecular dynamics can help is by studying how drugs bind to particular proteins. Okay, so you can take a particular protein, you can expose it to a certain drug, and then you can see how a particular drug is binding to that protein. Okay, so now these are all models, right? So since we have never seen a protein structure, we only solve it indirectly using X-ray crystallography. So a protein structure is a model which helps us predict the behavior of a protein. So remember, in the start, I tell you that a model is something that is going to make predictions. It is something that looks at observations and translates them into predictions, right? So just like that, by modeling proteins or protein structures using representations like this, or the ones that I've shown you earlier, we have been able to see that do drugs bind? Do proteins bind other proteins? Do proteins behave in certain ways? And by looking at computational results and by comparing them to results predicted by experiments, we have found that they agree. And that means that by modeling proteins using these kinds of atomic representations is sufficient for the purpose of finding new drugs and for the purpose of looking at protein-protein interactions, or if the protein is an enzyme, how does a protein bind to a particular substrate, okay? So all of these mechanisms can give us results. But remember, again, that the models have limitations, and you must be aware of those limitations when you are using them. So with this, I will stress more. For example, when you are doing molecular dynamic simulations, you need to prepare your system. You need to have the right kind of input files. And at that point, there are probably like 20, 30 decisions that you have to make, right? So for example, are you using the correct description of your system? Do you have the right amount of water around your protein? So in this case, I am not showing any water molecules. But if you look at this particular animation, you will notice that there are a lot of grainy particles on your screen in the surrounding. This is not noise. These are basically ions and solvent particles that are moving around, right? So that is basically solvation. Then you need to decide on certain things such as cutoffs and which algorithm. So when you do molecular dynamic simulations, there are about 10, 20 algorithms that you can use at different stages of your simulation. Now, based on what you are trying to study, how accurately have you modeled it using your model, whatever approach you're going to try and use. All of that needs to go in when you are doing system prep. Just don't pick up somebody else's model, which they have used for a different protein, and do not use it blindly for your system, because chances are that they have optimized it based on their protein, which is being used to explore a different system. And your system is completely different. Your protein is completely different. It is going to do a completely different task. So chances are that you will need to do certain changes in these to best reflect your own system. Okay. So then there are other things that you must look at. So for example, when you run a simulation, how long are you going to run that simulation for? If you have supercomputers, you can run it for very long. If you have a desktop, which I don't recommend for using molecular dynamics simulations, but if you have a desktop, then there are chances that you won't be able to run a very long simulation, right? So you may have shorter simulations and you may have longer simulations. And the kind of conclusions you can make highly depend on what is the length of the simulation that you want to uh, uh, run, right? So, for example, if we are looking at drug binding, this kind of phenomena might not be visible if you run a very small simulation. So you will have to run a very long simulation for the ligand that is free in the system to diffuse and for the entire protein to change its conformation and lock that ligand in. This kind of structural conformational change requires large scale simulations. Okay. So to derive any kind of statistical properties from your system, thermodynamics, obviously, you will thermodynamical properties from your system, you will have to make sure that the kind of analysis that you're doing, how sensitive is that analysis to the length of the simulation. Okay, so maybe you can report that, we ran a simulation for 10 nanoseconds or for 1 second, and we did not see this drug bind to a particular protein, and somebody else with a much bigger supercomputer might be able to run it for, let's say, 3 seconds, and in the extra time that they have run it, they might have seen that the drug actually does bind. Okay, so you have to be very careful that when you are writing a paper, that when you try and derive any conclusion, what is the method that you're using, and can that method be used to make that conclusion or not? Okay. So with that, I think I'm already over time. So I'm going to go through a very quickly, without explaining too much of a use case, um, uh, just to give you an idea, right? So we have, up till now, we have looked at what does a model look like? How does one make models? What are some examples of biological models? And how do biological models operate in the context of molecular assemblies? Okay, so now we're going to develop a model for a different kind of a problem. Okay, so I want to introduce, I know most of you might already be familiar that phospholipids make up bilayers, and these bilayers then wrap up into arrangements like this called liposomes. These kinds of arrangements are also what your cell is made of, right? The cell membrane. So the cell membrane has phospholipids, right? And then you might have arrangements called micelles where you only have one layer which wraps onto itself. You don't have a layer on the inside. Okay. Now, these phospholipids have particular properties that the head group is actually hydrophilic and the tails are hydrophobic. So based on these properties, these bilayers self-assemble because the tails want to get away from water and the heads like water, so they automatically get packaged like this. Okay, but why do we want to study membrane? So for example, if you look at this figure at the bottom here, this gray is a biomaterial implant. So it might be a hip replacement, it might be a shoulder replacement, it might be plates inserted into your body to mend broken bones, or it might be a dental implant. Okay, so all of these kinds of implants, when they are done, they trigger certain kind of responses from the body. Okay, so because when you put something foreign into the body will detect it as foreign, and what will happen is that the body will create will trigger an immune response. And you might hear that not all people who have um, implants actually accept implants. some of the implants get rejected. And the reason why they get rejected is that the body is able to identify it as a foreign body and start attacking it. Okay. So what you want to do is you want to find out what kind of a material should you use so that it will not trigger an immune response. Okay. Now to do that, we have to focus on the bilayer. So one of the reasons why the immune response is triggered, what happens is that this liposome, for instance, is going to get ruptured, right? So when it ruptures, it leaks its inside out, which triggers the immune response. So what you want to do is you want to study these polar arrangements, these phospholipids, and you want to find out what materials are those which do not affect, which do not cause rupturing of the membranes. Okay. So now, if you want to create an assembly like this inside a computer, you want the heads to face away from each other, and you want the tails to face each other, right? So if we want to create models, we want either this to happen or we want this to happen, but we don't want this, because outside is water. So water should repel the tail. So the tail should come on the inside like this, not like this. So I've written depends here because if the outside, if on the outside you have, for example, something that is non-polar, like water is a polar solvent, right? So if you have a non-polar solvent, then what will happen is that the head groups will like to see each other and the tails will be on the outside. But for this purpose, we are going to consider this as an incorrect arrangement, and we are going to look at this and we're going to think of these as correct. Okay. So this means that we can assign a vector, and that vector points towards the head. Okay. And we are going to do something called coarse graining. So what does coarse graining mean? So coarse graining means that we're going to assume that there are pieces of the membrane, and these pieces are going to come together. So we're not going to study this individually, but we're going to study this in groups of 20, for example, or 12 or 15. So 1, 2, 3, 4, 5, 6, 7. 7 are on the upper leaflet and about 7 are on the lower leaflet. So each of these patch contains about 14 um, bilayers or 14 phospholipids, right? And what we want is we want them to come together like this. We do not want them to come together like this. I just showed you, because if the heads are going to face the heads, they are not going to make the bilayer, right? So what we want is we want to create a sort of arrangement where if I package this into a ball and into a sphere, and if I package this into a sphere, I can assign directional vectors to each of these. Okay. And then there are going to be distances between their centers. So what is happening here is that when the two vectors are arranged like this, the angle between them is 0. And when they are arranged like this, the angle between them is 180 degrees. So what we can do is that we can assign a penalty function which does not penalize this arrangement, but which penalizes this arrangement. So now we have to look into mathematics and we have to find out something that is sensitive to the angle. And we find that out very quickly. We look at the cosine function and we see that the cosine function is 1 when the angle between two vectors is 0, and the cosine function gives you -1 when the angle between them, does it? Actually, I don't remember. I think I might have drawn this incorrectly. I will look into this again. But remember that what I'm trying to say here is that the cosine function changes with angle. And what we can do is we can use this cosine property as a penalty function um, to categorize that we want this arrangement to be favored and to get the highest value, and for this arrangement to get the lowest value. For now, I'm going to assume that this graph is correct, and I don't actually remember whether cosine of 180 degrees is -1 or not, but we're going to assume for now that it is. And if that is accurate, then we get a -1 when the angle between the two is 180. So with this, what we can do is we can come up with arrangements where we can package. So each of these spheres has about 14 phospholipids inside it, right? And this line shows the direction of the heads. So the heads are pointing down and the heads are pointing up. And then you can make arrangements like this. And you will notice this black patched line, right? And what this black patch line is showing you surfaces. And by approximating cells as membranes, and by approximating membranes using these spheres, what we have done is that we have created a model where now we can change the properties of this black surface to find out which surface is going to create a rupture uh, in the membrane. And you will notice that when the cell, so this is representing a cell membrane, which is coming and it is flattening out. By changing the properties of this surface, you can break this bond or this interaction. And if this interaction breaks, what will happen is that the contents of the inside of the membrane will leak out. So this use case demonstrates that if you have a problem and your problem was which materials trigger an immune response and which material do not trigger an immune response, what you saw here was that we developed a very simplified system. In this case, we do not need MD simulations, right? We do not need to track atomic level changes in the phospholipids. By approximating, what I've done here is, I did not get a chance to talk about it. What I've done here is that on the left-hand side, this is the normal phospholipid. And what I have done is I've packaged this top as the polar head and the two tails as this. And then I have packaged 14 of these into a sphere. And this sphere is then what I then simulate here and find out properties of my system. And we can find out surfaces which do not create immune responses. So with this is my concluding slide. What are the takeaways? So one of the challenges, for example, right now is protein folding. Okay, so we don't know which sequence will change into what final protein structure. Okay, and what we do now have is a tool called AlphaFold. For example, this is a recent, actually it came out in 2018, but the latest improved version is fairly recent, AlphaFold 2. And what it does is basically it uses machine learning AI methods to actually predict from a sequence what the final structure is going to look like. Okay. Now, I did not talk about this because it is not important how AlphaFold works. But what is important is that the AlphaFold is based on a model, and that model has limitations. And if you have limitations in the model, you cannot blindly trust, which a lot of people right now are doing using AlphaFold, is that they think that the AlphaFold is going to give them 100% accurate representation of their system, which it does not. And this is what I said before, that what people do is they use models as black boxes. And that is something that you should always avoid. Okay. So one of the current challenges is that when using AlphaFold, be absolutely sure how AlphaFold works and make sure that the output is reasonable, right? The other thing that I wanted to stress on, and which I want you to take away as a takeaway, is to have a complete understanding and identify and work with the limitations of your model, and do not work with it as a black box, because it is always going to have limitations. and you don't want your results to be actually wrong. I am so sorry I went 20 minutes over time, but I was given that our talk could be 1 hour, 1.5 hours. So I thought, why not push it? So I think I have covered comprehensively. Um, like I tried covering comprehensively the whole scope of this topic, modeling of biological systems. I hope you people have learned. Now the floor is open to questions. So does anybody have any questions?
Thank you, Dr. Ashar Malik, for the nice presentations. Okay, anybody have? Hello.
Any questions, anyone? No questions?
I have a question actually.
Sure. Go ahead.
In MD simulations, there are some type of water model.
Yep.
Like SPC, TIP, 3P, and others. And how to choose the water model that's suitable with our system or our simulations?
So there are two ways to answer this question. One is that when you talk about a single point model versus a 3-point model. So a TIP 3P model is where, so let me just try and go back. I think I have a figure here somewhere which can explain. So when you talk about water molecules, SPC model looks at a different way in which the 3 atoms are packed together, and the TIP 3P looks at it in a completely different way. Okay, so when you are, for example, using the charm force field to analyze, you should definitely go with TIP 3P, because as far as I can recall, SPC is not explained inside charm force field, right? So you should also know that there are different reasons for these different water models to be out there. Computational simulations are not accurate. Some people saw that in certain cases, water needs to be described in this way for it to have results which match closer to experiments. In some other cases, people thought that TIP 3P is a better model and it gives us a better prediction that matches very closely to reality, right? I have always used TIP 3P. I will always recommend using TIP 3P. But remember that there is a whole range. You can either use implicit solvent. So in implicit solvent, you have no waters at all. You actually use a continuum, more like one value which approximates the entire space. Okay, or you can get better values if you have single point, or if you have 3-point, or if you have high, because I think there is a 5-point model as well. I don't know the details of it, but what actually happens is that the electronic distribution around this in TIP 3P is such that you have positive and negative charges, which can help you better build this kind of arrangement if you have a solvent, right? So if you have other kind of water models, they might not be able to replicate certain real world phenomena. So just be careful. I can't give you an answer which to choose, but literature will help you do that.
Okay, thank you. Okay, anybody have questions?
Yes, Mr. Umar.
Okay.
Hello.
May I?
Hi.
Okay. Thank you, Dr. Ashar Malik. Thank you for very nice presentations. I'm just interested with the usage of machine learning or AI, as you mentioned about the AlphaFold, because it's kind of a modern way, the conventional way. We decide the structure, and then we try to close to the real situations. But in machine learning, we use the some method to define the best way to get the model. So what do you think about the future of the usage of AI? It can be used for specific model which is better than the conventional way, or is there any limitation about the usage of AI in the building of the best model for the specific functions? Thank you.
Okay, so yeah, so thank you for that question. This is a very tricky question to answer, and I can't give you a direct answer, right? So let me try and explain why people have recently started using AI a lot. So what has started happening is that the basic reason is that there is a ton of data available. So the growth of data plus the increase in computational power, these are the two variables that has led to us using AI ML methods. Okay. Now, what has happened is I told you about first principles. So in a lot of cases, we'd have no clue how things are working, right? So what AI ML does is it helps us bypass the step of us understanding and building a model, right? So
Yes.
what we usually do in AI ML is we have a ton of data. The data has certain features. It has inputs, it has outputs. And what we try and do is we try to create a black box, and we say that, hey, black box, can you find a weighted average function which converts this input to this output, right? And what ends up happening is that when you train that model, this is not the model which actually explains your system. It is a model which just turns the input to the output.
Yes.
Okay. So with the increase in data flow, with the increase in compute power, what we have done is we have started looking at shortcuts. And AI ML is a very powerful tool when it works correctly, right? But a lot of time it can create problems, right? So I don't have okay, I was just looking at AlphaFold earlier. So I'm just gonna take this time, a few seconds, to explain something. So this is a P53 structure of the protein P53. Okay. So what happens is that when AlphaFold gives a prediction, there is a color code associated with how confident you are with each stretch of the output.
Okay.
Right. So in this case, when you see orange and when you see yellow, you have low and very low confidence. And this central core part is blue. Right. Now, what has happened is that AlphaFold has learned from existing protein structures. So the protein structure corresponding to this sequence was not present in PDB database. The structure corresponding to this blue part was present.
Okay.
Right. So what the AlphaFold has done is it has helped people who don't know how to predict structures, that it has given them a shortcut. Again, you input a sequence, it is going to produce a structure like this. And then people who don't have an understanding, what they're going to do is they're going to trust that this is the correct structure. But in reality, what AlphaFold is doing is it is learning from known data or existing data, and the data that was existing is only in this solid blue part. Everything else is guesswork. And if you tell me to trust AlphaFold's output, I will look at the structure and I will tell you, no, I don't trust it.
Okay.
Right. So there are going to be, you have to, go back to that thing that, understand what the model is doing, understand its limitations, understand what it can and cannot do, and then only trust its output.
Okay.
So as regarding your question, what is the future of AI? It is going to be used increasingly. Everybody's using it. The only trajectory I see is going up. So for people who don't know AI, you should learn it because it is going to help improve your career chances, getting good jobs and stuff. But remember that it is not actual science. So when you use AI, you are using information flow to convert. So it's informatics. It is not. I mean, people might get angry at me when I say AI ML is not science, but basically you're just using information flow.
Yes. Yeah, okay.
So
using the data.
Yeah, exactly. Okay. So I hope that addresses your question in some way.
Yes. Thank you very much.
No worries.
Interesting question, interesting answer.
Yeah. So
Okay.
tricky.
It's tricky.
Yeah.
So any other questions, anyone? Anything you guys want to discuss? Otherwise, you have my contact on Twitter, which I showed in the slides a few seconds ago. So I'm just going to go back to the final or the first slide probably. So you can reach me on Twitter. My contact details should be with Umar. You can obviously, ask him if you want to get in touch. If there is anything you want to discuss about your own research, I'll be happy to help out in any way I can. So I guess since there are no questions, Umar, I think we should call it a day.
Okay. Before we finish this sessions, I think there is we have a certificate that. Wait a minute. Okay. Yeah. I hope you and everybody have already seen the certificate. This is a certificate of appreciations certified awarded to Dr. Ashar Malik in recognition of his contribution as speaker in IPB Visit Talks. Thank you, Dr. Ashar Malik. And I will, okay, and I will summon Dr. Akhiruddin Madu. Dr. Akhiruddin Madu is our head of divisions in biophysics in physics departments. He will give the closing statement. Dr. Akhiruddin Madu, can you hear me?
Ya, oke. Selamat,
Thank you.
Ya, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon. Thank you very much, Dr. Ashar, for the exciting talk today. I think there are many interesting ideas from this talk that can be developed at the Department of Physics, IPB University. Especially a topic about biomimetics is one that is very interesting to be developed further at Department of Physics, IPB University. The Department of Physics, IPB would like to thank Dr. Ashar. We hope this event will be an inspiration for us for further development at the Department of Physics, IPB University. We hope this event today will be the beginning of further cooperation. Thank you and good health always.
Okay,
Thank you so much for having me.
Okay, Dr. Ashar Malik, do you have any closing statement?
No, just just be careful when using models.
Yeah.
I think that's all I would have to say. But thank you so much for the organizers. Thank you, Umar, for getting in touch with me and putting all of this together.
Okay.
And I hope that I can stay in touch with researchers at the physics department at IPB for potential future collaborations. So thank you.
Thank you. Okay, so we will closing this physics class with Hamdalah, Alhamdulillahirabbil alamin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Ashar.
Thank you. Okay, Ferry, as you can end meeting. Thank you, Dr. Ashar.